recording at the end. We'll stop the recording at the end of the main talk, so you should feel uninhibited to ask Dobie any tricky questions you'd like without them being committed to tape. We have, as Consciousness Club regulars will know, we have a slightly longer slot than the normal seminar, so we have an hour and a half, and that's to ensure we get plenty of time for Q&A after the talk. So without further ado, it's a real pleasure today to introduce our speaker, Dobromir Rahnev. So I've known Dobie for quite a long time. I guess since he was a postdoc and I was a postdoc well, when he was a PhD student and I was a postdoc in New York. So Dobie did his undergrad in psychology at Harvard. He then went on to do his PhD in psychology at Columbia University with Hak-Kwan Lau, and that's where he got interested in consciousness and metacognition and did lots of cool work as a PhD student. And then he went on to do a postdoc in cognitive neuroscience at UC Berkeley with Mark Desposito before joining Georgia Tech as a faculty member, and where he's now associate professor and runs his lab looking at perceptual decision-making, metacognition, and all things connected with that. And he's got a whole string of awards. I won't read them all out, but most recently he was awarded the American Psychological Association Early Career Award. So that's a really prestigious achievement. So Dobie, we're really excited to have you with us and to present. So I'll hand over the floor to you.
Thank you, Steve. That was really generous of you. And thank you again for the invitation. This is a wonderful talk series. I really enjoy joining when I can, when it's not super early in the morning here in the US. So today I want to tell you about some of our work on modeling visual metacognition. And as Steve mentioned, the interest in of my lab is really in perceptual decision-making. And the way we conceptualize a perceptual decision-making.
Dobie, we can see, sorry, we can see the, it wasn't like it was before. So we can still see presenter notes.
Okay. Let's see. Let me stop sharing. Let's try again. Let's do it this way.
Yep.
Okay.
Yep. Cool.
All right. So the way we conceptualize perceptual decision making is as a process that has really several components. So you start with a stimulus out there in the environment. It can be, external to you. It can be internal. It can be your own body state. But there's some sort of a stimulus out there. That stimulus gives rise to an internal representation, and then based on this internal representation, you make a decision, and then possibly you can evaluate that decision. So to us, this is all of these four components are just integral to perceptual decision making. In order to understand one of them, you need to understand the others, and you can't really study any one of them in isolation. So in my lab, we study all four of them, and I'll just briefly tell you a little bit about what we do with the first three components. So with the stimulus, we usually use sort of the standard Gabor patches and random dot motion stimuli, but we actually are starting to think more and more that these are probably not the best stimuli to use for perceptual decision making, and that you may want more complex stimuli, like in this particular study that we did, that allows you to do multi-alternative decisions. So this actually is some development just in the last couple months in my lab, where we think that we have a new stimulus set that can tell you actually what the internal representation is. And this is not the case for the Gabor patches and random dot motion, but this is really new stuff. So I'm happy to tell you more if you want to know, but I'm not going to say anything more about it right now. So once there's a stimulus, that stimulus gives rise to the internal representation, And in a way, I think this is really the holy grail of studying perceptual decision making, knowing what is the internal representation. When we study metacognition, when we study decision making, perceptual decision making, we oftentimes just assume an internal representation, and we don't necessarily, make sure that that's the true internal representation. And in many ways, this is the most important part, trying to figure out how stimuli actually internally represented, and is the most difficult part. So within this component, we've done several sort of lines of somewhat unrelated work, actually. So we're working on whether the representations are probabilistic or not. So we have some empirical work, and we have some theoretical adversarial collaboration going on. We've done a little bit of work on the Drew diffusion model, and we think there's some limitations to that model that have not been recognized before. And with a former postdoc of mine, we have a series of studies on how after perceptual learning, there's a wake reactivation in the primary visual cortex. So I can give a separate talk on each of these three things, but I'll just mention it here and move on. So once you have the internal representation, that still doesn't automatically give you a decision. There needs to be a process that actually forms a decision based on that. And we're, again, interested in all parts of that. So how do we actually make decisions? So we've done work on suboptimality in perceptual decision-making, on different biases, on how expectation, attention, cognitive control all influence this process. All right, but what I really want to talk to you about today is that last part, evaluation. So here's the outline. I'll tell you about metacognitive noise, then I'll tell you about how we have been relating measures and models of metacognition. Then we'll talk about comparing models of metacognition, and I'll finish with the most speculative part, where I'll try to answer the question, or at least speculate on the question, is the metacognitive system separate from the decision system? All right, so let's start with metacognitive noise. So the title of the talk was Modeling Visual Metacognition, and one of the things that we really care about in my lab is trying to create a good model of metacognition. And when you think about modeling, there's usually some sort of a target effect that you want to start with, that you want to explain. And there's many more possible target effects with metacognition, but we think that the most important one is the basic observation that metacognition is inefficient. Now, what does that mean? There's a number of different ways to sort of conceptualize of what is metacognitive inefficiency, but the one that I like the best comes from signal detection theory. So using signal detection theory, you can compute what we call stimulus sensitivity, just this measured D prime that is computed from choice data. And as probably most of you know, you can also compute meta D prime, which is metacognitive sensitivity. And it's a very similar measure to D prime conceptually. It's just that it's not computed from the choice data, it's computed from the confidence ratings. But it's in the same units as D prime, and it measures the same kind of sensitivity. It just that it's not from the choice, but it's from the confidence. So then what you can do is you can divide these two, and you can get a different measure called M ratio. So that's just meta D prime divided by D prime. And the empirical finding here is that very frequently this measure shows as less than 1. So this means that there's some information loss in confidence ratings compared to the choice data, or in other words, metacognition is inefficient. All right, so how do we then go ahead and model that metacognitive inefficiency? Well, there's a pretty obvious solution that many people have converged on, which is to postulate the existence of metacognitive noise. Metacognitive noise is just simply noise that affects the confidence ratings, but not the decision, right? So there's the sensory information is corrupted by noise, but there's going to be separate noise that only affects the confidence. Okay, so if you postulate metacognitive noise, what does a model look like? So here's the simplest possible model that you can create. You start at the stimulus level with two stimulus classes, S1 and S2. Let's say they're Gabor patches of different orientations, but obviously the stimuli can be anything. Then you postulate the existence of sensory noise. And then at the decision level, you have Gaussian distributions. So at the stimulus level, the stimuli are perfectly distinguishable, but at the decision level, they're not perfectly distinguishable anymore. And the term representation is just normal distributions with a given mean and with the variance that comes from this sensory noise. So far, this is just standard signal detection theory, nothing interesting, nothing new. This is over 50 years old stuff. Now, if you have to postulate metacognitive noise, then you just say, well, there's one more stage of noise. There's metacognitive noise here. And then at the meta level, this is where you place the confidence criteria. And at the meta level, now you have representations that are, again, the Gaussian distributions. They have the same means. So the means of each distribution is the same, but the variance is higher. So the variance at the meta level comes from summing the sensory noise and the metacognitive noise. So think about the model this way. What we have done here is we have added the metacognitive noise to the signal itself. And this is the way we have been thinking about it before. And this, I think, the way most people think about this model. But I do want to say there's an equivalent way of thinking about this same model where the metacognitive noise is added to the criteria. So how would that work? Well, you start with the same, in the same way. You start with the stimulus level and the decision level, but then you stay at the decision level and you place the confidence criteria at the decision level, except that you don't make them stable, but you make them themselves a distribution, right? So now the confidence criteria themselves vary from trial to trial, and if they vary with this noise, so the metacognitive noise would just be the variability of the criteria. These two models are actually mathematically equivalent. There's no difference mathematically between these two models. You cannot, based on this model, you cannot say whether the metacognitive noise is added to the signal or to the criteria. Both interpretations are perfectly valid and equivalent. All right, so great. So we have a really simple model of metacognition that has a metacognitive noise to it. This model does do anything more interesting than just make metacognition inefficient. And it turns out that it actually does. You can derive a prediction of the model that, at least at first, we thought was very much non-intuitive. So here's how this works. So within this framework, D prime is just computed as mu2, so the mean of this distribution minus the mean of this distribution divided by the standard deviation here. So this is just the standard computation for D prime. And you can do the same thing for meta D prime. So the meta D prime would be just D prime, but at this level. So it's the same two means, but the standard deviation is given by this formula. And now if you to divide, if you to get meta M ratio, which is meta D prime divided by D prime, what you get is the numerators cancel, and you get the sensory noise divided by this sum of the variances of the sensory and the metacognitive noise. So the interesting thing about this expression is that it's an increasing function of the sensory noise. What does that mean? As the sensory noise increases, M ratio would increase. The reason is, as you increase the sensory noise, both the numerator and the denominator increase, but the numerator increases faster than the denominator. So I'm plotting it here for you. So this M ratio, this is this expression here on the y-axis. This is sensory noise on the x-axis. And if metacognitive noise is 0, this always stays at 1. There's no metacognitive noise, so this just cancels, it becomes 1. But for positive metacognitive noise, as you increase the sensory noise, you get higher and higher M ratio, right? So this is just hopefully convincing you that this is true, that as you increase the sensory noise here, you get higher M ratio. So then we get an interesting model prediction. The model prediction is that I'm going to frame it in the negative. Decreasing the sensory noise would decrease metacognitive efficiency M ratio. When we first thought about this, it sounded very counterintuitive, but when we said in a grant that this is counterintuitive prediction, people were like, no, it's not counterintuitive. So now we call it a unique prediction of having a metacognitive noise, because whether or not it's counterintuitive, I guess it's very subjective. So how do we test this? How do we test this prediction? So here's the paradigm that we used. It's a really simple task. It's just 2 IFC, 2 interval force choice. So in the first interval, there's either Gabor, no Gabor. In the second interval, there's a Gabor, no Gabor. The Gabor appears in one of them. Then people just indicate in which interval there was the Gabor and then give a confidence rating. The task is really not very important. So conceptually, what is important here is that high noise, high sensory noise, really the way to conceptualize that is as a lot of variability in the internal representation, right? So you have Gaussian distributions that are more spread out. So intuitively, from trial to trial, you get a lot of variability. So using the same stimulus, trials are more dissimilar. And we're thinking, how do we make trials either more dissimilar or more similar? And we thought that perceptual learning would do that. So perceptual learning would make trials more similar over time. So as you are exposed more and more and more to the same stimuli, your internal representation will be more consistent. So there'll be less sensory noise. So that should decrease the noise. So what we did was we did 7 days of training. And this is work of my former postdoc, Jiwan Bang. So what did we find? Well, after during the 7 days of training, we saw that the threshold for the stimulus intensity decreased. So we needed lower and lower threshold in order to achieve the same performance. So this sort of really shows that sensory noise is decreasing as we sort of hypothesized. Conversely, D prime is increasing. So people are getting better at the task. Confidence is also increasing, not surprisingly, if D prime is increasing. And now the critical thing, what happens to M ratio? Again, because the sensory noise is decreasing, we would predict that M ratio would decrease, and it's actually exactly what we find. So the prediction of the model seems to pan out really well here. We did a couple more studies in that paper, and I'll just tell you about one more, where we asked whether this perceptual learning effect can appear on a really fast timescale. So we call it ultra-fast learning. And we're trying to answer the question, do the same effects appear not on the order of days, but on the order of minutes? So how do you do that? Well, here's how we did it. So this is how normal experiments work. You have a whole bunch of subjects. In this case, we have 178, and then each subject does a bunch of trials. And the way you usually analyze that data is you look at one subject, you look at all the trials, then you compute D prime, you compute M ratio, you compute average confidence, you compute whatever you want to compute. We call this standard subject-based analysis, and most people just call this analysis. Right? This is just what we do. But you can probably already see where I'm going with this. You can actually do something completely different, which is ignore the fact that these are different subjects and just compute D prime, M ratio, whatnot for the first trial across all subjects. Then you compute the same thing for the second trial, for the third trial, and so on and so forth. So do the analysis in a trial-based manner rather than a subject-based manner. Now, there's all kinds of issues of doing that kind of analysis, but because we're comparing trials and it's the same collection of subjects that, they have different sensitivity, they have different biases, they have different everything, but it's the same different for each trial. So it's actually, we've done a bunch of simulations to show that this is actually a reasonable thing to be doing. So this is conceptually what we did. We used two different tasks. One was what we think of intuitively as a detection-based task. So here people need to say whether a Gabor patch that is embedded in a ton of noise is oriented 45 degrees clockwise or counterclockwise. So this is probably a little hard to see. This is what subjects actually show. So this is this orientation. So this is the counterclockwise orientation in this particular trial. And we also did what we think of discrimination-based task. So in a detection-based task, it's really hard to see what is there, but if you see it, then it's super easy to make the choice. Versus in the discrimination-based task, it's very easy to see the Gabor patch, but it's very hard to say whether it's clockwise or counterclockwise from vertical. So we used orientation that is less than 1 degree of vertical, and this again a left orientation. Probably hard to see, but you can take my word for it. This is tilted to the left. So again, we had 178 subjects, 97 trials per task per subject. So for each task, we had 97 trials. So what did we find? We found that over the course of the 97 trials, D prime increased, as you may expect. So people are getting better, not just with perceptual learning over the course of days, but even within 97 trials, they get better. And as D prime increases, M ratio decreases. So the same effect we see again. As the sensory noise is decreasing, so does M ratio decrease. This for detection-based tasks, these are pretty large effects. For the discrimination-based task, we saw actually a much smaller increase in D prime, and correspondingly a much lower increase, a much lower decrease of M ratio. And we can even compare between the two tasks, and there was a significant difference, so that this is a much steeper increase compared to this. And correspondingly, for the detection-based task, M ratio had a much steeper decrease compared to the discrimination-based task. So overall, this seems to be pretty good evidence that it is indeed true that as you decrease the sensory noise, you decrease M ratio, which is providing evidence for the existence of metacognitive noise. So
can I ask just a quick question? So
absolutely.
Can you dissociate D prime from sensory noise here? So because I noticed in your first plot, it looked like there was a change in D prime that wasn't reflecting the change in M ratio, which was more linked to the change in the contrast parameter. I'm just wondering whether you can pull those three things apart.
Yeah, so it's a great question. So it is an assumption that what is driving the D prime increase is a decrease in sensory noise. We think it's a reasonable assumption, and it's supported by prior literature, but it is an assumption. And that's why we have a number of different ways of testing it. But you're absolutely correct. We cannot prove that this increase in D prime is driven by sensory noise. We think it's a reasonable assumption, but yeah, we can prove it. Then again, if it is caused by something else, I have no idea how you would explain the M ratio decrease. Maybe it's possible, right? I mean, yeah. So intermediate conclusion here, metacognitive noise makes no predictions that are confirmed by the data. So to me, this is really good. So metacognitive noise was something that we just used to add to the models just so that they can fit the data. But it seems that it actually does more than that. It can actually make predictions, and then we can see those prediction data. So this is very encouraging to us. Maybe this is a good time to take other questions if there's any for this part.
I actually do have a small question, so it might be super obvious, but why did you pick to manipulate sensory noise as a learning thing and not just as contrast or something more straightforward like that?
Yeah, this is a great question, and this is where what I was saying earlier about the internal representation being the holy grail comes back to us. You think intuitively that if you increase the contrast, or if you decrease the contrast, that would affect the sensory noise. But we actually did a lot of thinking, a lot of work on that when we were doing this project. And we actually think that's not true. We think that if you change the contrast of the stimuli, you're still affecting the means of these distributions. So you're still affecting the signal, you're not affecting the noise. Intuitively, it may seem like that's what you're doing, but that's not actually what is happening. And the thing is, there's no proof either way, because we don't know how stimuli map onto the sensory evidence. So we can't, that's why it's so frustrating, right? To work with these things. You need a manipulation of one component, and you just don't have it because you don't know how your stimuli map onto the internal representation. And that's why I'm so excited about this new stimulus set, where we think we have a bit more of a handle on that. So we may repeat some of these experiments if that actually really works. Maybe one more?
Yeah, let's take one more and then maybe Karen. Yeah, Chris, go for it.
Yeah, I have a quick question, sorry, Scanner. I was just wondering what happens to measures of bias or criteria with the addition of the metacognitive noise. I was just trying to work it out and couldn't quite get my head around it.
Yeah. Yeah, I don't think that too much happens. So if you're biased for the decision, so metacognitive noise doesn't affect the decision part at all. It does affect the confidence rating. So if the same criterion in the presence of metacognitive noise, it may get whether or not you assume that it exists or not, it may shift the confidence criterion a little bit in terms of what is being estimated. But I don't think it has much of an effect on those parameters.
Thanks.
All right, so we have a decent model that does some interesting things. It makes predictions and they pan out in data. But what we have been thinking afterwards is how to relate measures and models of metacognition. And let me tell you why this is so important to us. So very generally, you can think of measuring a phenomenon and you can think of modeling a phenomenon. And oftentimes these things are thought of as completely separate things, but it should be recognized that they're actually very strongly related. So this comes from early work on, work from like what is now probably 30 years ago, signal detection theory by Macmillan, who showed that a lot of measures that were thought of as non-parametric measures of performance turn out to be completely parametric. So if you take them seriously, then they imply a model of decision making that then it becomes a parametric measure. So the measure becomes a parametric. So measures very often actually imply a model. In the same way, once you have a model of phenomenon, that very often implies a measure. So if you try to study these two things separately, you're losing something, right? Because your measures, you don't know what models they're implying, and your models, you don't know what measures they're implying. So how are we doing in terms of this stuff in metacognition? Well, we have a whole bunch of possible measures, from the difference between confidence for correct and incorrect, to correlational measures, type to area in the curve, to the newest measures, meta D prime and M ratio. And, they all have their, good and bad parts. And then we have a whole bunch of models of metacognition. This is just a selection of them. And you think that some of these things would be related. You think that some of these models, some of these measures are related to some of these models, and some of these models imply some of these measures. But it's actually not true. Not a single one of these measures is related to not a single one of these models, or vice versa. So we definitely are missing something in the field then. So we thought that this is actually a great opportunity to try to make this connection. So our approach here was to test psychometric properties of current measures. We thought we'd start with the measures that we have that running with the models that we have, and then we try to derive a better model, and then maybe a better measure. So this is the existing measures again. What kind of psychometric properties would you want to test? Well, there's many possible things you could do. Probably the most obvious one is to test for accuracy on the task. So are these measures independent from accuracy on the task? And this is actually a very well known finding from Steve and Hakon had a paper in 2014 that was talking a lot about these issues. Really, only M ratio out of all of these 6 measures is largely independent of accuracy. The first 5 measures, they're all very strongly dependent on accuracy. So as accuracy on the task goes up, those measures go up. So, that's not a great psychometric property, but M ratio is pretty good here. But another thing that we have not really done much with in the field is metacognitive bias. So if one person has higher confidence than another person, or in one condition you have higher confidence than in another condition, then what happens to these measures? And we really don't actually know. So we thought let's find out. So here's a task that we use, another Gabor patch task. All of the tasks that I'm going to show you today, I think use Gabor patches. Just orientation discrimination, is it left or right, a vertical. And here we collected confidence on a continuous scale. So from 100% sure that it's a left orientation to 100% sure that it's a right orientation. We got 20 subjects, a lot of trials per subject, 2,800. So these 3 different sessions. So we really need a lot of data in order to do the modeling right. And we had 3 contrast levels, so 3 different difficulty levels. And this is work of my former graduate student now. Unfortunately, she graduated and she's actually now at UCL. So you should say hi to her. She's in Ray Dolman's lab. All right, so how do we analyze that data? So this is our continuous scale. And the way we would analyze it, we would place criteria at a specific place, and then we would recode the scale as 1 is the low confidence, and 2 is sort of the outside of the scale for high confidence. Then we would move these criteria to a new place. Then we would do a different recoding. We'd move it again, and we just sweep this criteria over the whole scale. And for each of these recoded confidence ratings, we would compute M ratio based on this recoded confidence. Just to be clear, this kind of recoding gives you the highest confidence because there's a big space for 2 for the high confidence measure. This kind of recoding gives you the lowest confidence, so this a big space for 1. That makes sense? Okay. So what do we find? So as you move the confidence criterion from the 50 to 100 location, you see that M ratio, meta D prime divided by D prime, tends to decrease, and that's the case for each of the 3 contrasts. So this is a significant decrease for each of them. And one more thing to notice here, the 3 contrasts, so this is the 3 difficulty levels, they're on top of each other, which sort of suggests that M ratio is not affected by difficulty, which is something that I mentioned already here. So an empirical demonstration of that. So that's again very good for M ratio that that's the case. You can do the same thing for meta D prime, and you see the same kind of decreases, and they're again all significant. We've done this for the other measures, and they show sort of weird effects there. They all depend on both contrast and on the confidence criterion location, but in weird and weirder ways. So let's just focus on M ratio and meta D prime. And just to mention, this is also true. So this is a within subject analysis. the same things happen across subjects as well. So you can correlate across subjects, and you can look at where people who are more confident also have higher M ratio. And this is work of my current lab manager, Kai Xue. And you can see that's true for 2 out of the 3 tasks that we tested. These tasks were taken from the confidence database, which sort of gives me an opportunity to advertise this a little bit. We still accept submissions to the confidence database. There's 150 data sets there, so that's great if you want to analyze it. But if you do collect new data, it would be great to keep growing that database. So please submit those new data sets that you guys are collecting. All right, so how do we model this decrease that we see we see that as you move the confidence criterion location to higher levels, you see a decrease in M ratio. So the standard segmentation theory just says, all of the confidence criteria are stable. That's clearly not going to do it. The Gaussian meta-noise model, which is the model that I told you about before, where the confidence criteria are now it's metacognitive noise in the confidence criteria, that's still probably not going to do it. So what we thought about is creating this new model that we call log normal meta-noise model, where the metacognitive noise is not Gaussian anymore, but it has this log normal distribution. Now the property, the log normal distribution has this really great property, which is one, it's bounded by 0. So in this case, it's bounded by the decision criterion. So it doesn't ever cross the decision criterion. These crossings of the decision criterion are sort of nonsensical, and they create big problems for the Gaussian model. But another thing that happens here is that the property of the log normal distribution is that as you increase the mean of the distribution, you also increase the variability or the standard deviation of the distribution. So naturally you get that the outside confidence criteria are noisier. So then we fit all 3 of these models. We use AIC, a Kaike information criterion. For those of you who are not familiar, an AIC difference bigger than 10 sort of indicates substantial support for one model over another. So we first compared log normal metacognitive noise versus just a standard segmentation theory model, so no metacognitive noise. And we see that the log normal model is strongly supported. Those are individual subjects. And you can compute that the log normal model is about 300,000 times more likely than segmentation theory in this data. You can then compare log normal meta-noise to the Gaussian meta-noise, and you see slightly weaker effects, but still in the same direction. The log normal model is 600 times more likely than the Gaussian meta-noise model. So it looks like it fits the data better. But what we really want to see is sort of a depiction of does it actually get these qualitative effects correctly? So again, here's the data that we had. And this is the predictions of the models. So standard segmentation theory just stays at 1, right? So M ratio just never changes. So that's not what the data shows. The Gaussian meta-noise actually shows a result that goes slightly in the opposite direction. So this is a qualitatively wrong prediction actually. And it's only the log normal meta-noise model that shows correct qualitative predictions. So this M ratio decreases for higher criteria values. Now it's not this shape here is slightly different from the shape here. Honestly, do we know that the shape is truly a log normal distribution? We don't. Maybe it's something else. But for us, what is the most important thing is that the noise, the metacognitive noise, increases for the outside criteria. So as you have more signal strength, as you have more evidence, those criteria are noisier. Martin, do you have a question?
Yeah, that's really nice. Dobby, I'm just wondering, could it be that some of the work here is actually done by trials where participants are detecting an error So they know they just made an error and they give like the lowest confidence rating, then this will be very, very, very reliable. And when you make the criterion, such that participants are very low confidence in general, then you lose this boost to metacognition by error detection, basically.
Yeah, so luckily in this experiment, I can confidently say that's not what's happening, because people are actually giving confidence and decision with the same button press. So if they make error detection, it's too late. If they give the response and they realize there's an error, they already gave the confidence with the same button press. So yeah, I don't think that's what's happening. And we've seen this, in other data sets as well. So this is a very robust finding.
Cool, thanks.
All right, so now that you have these models with metacognitive noise, you can now think, well, we have this parameter, metacognitive noise, right? Sigma meta. Can we use this as a measure of metacognition? Oh, another question, yeah.
Sorry for asking this late. So what I'm getting is when you increase the metacognitive noise, the M ratio drops, and it seems like that the value of metacognitive, like M ratio, depends on the value of bias, metacognitive bias. Am I right?
Mm-hmm. Yes.
So do you think this is a feature of metacognitive system, or it's a feature, this happens because of metacognitive system is like that, or this happens because it's as the result of the M ratio itself? For example, if we have another measure, like a new measure, we may not see this effect.
Yeah. So that's a great question. So it's hard to know. Is the honest answer, as in it's hard to prove one or the other. But I strongly think that what is happening is that it is an issue of the metacognitive system. So M ratio is correctly telling you that you have less information. So the confidence ratings are less informative when you use a high criterion than when you use a low criterion. And we've seen this, you can use, you can look at ZROC functions, and we do that in the paper. I'm not showing it here, and you see the same kinds of effects. So what I think is happening is that, yes, if you use a higher confidence criterion, the confidence ratings are actually less informative, and that is correctly captured by M ratio. But you may still want to have a measure that doesn't show this bias. If you have a measure that doesn't depend on the bias of subjects. Maybe
Thanks.
one more, and then I'll go continue.
Yeah, let's take one more, if it's a quick one, and then we'll carry on.
I would have asked you if it's okay if I state the question right now, because usually they are in the end. I was a bit puzzled when comparing the results from this experiment to the previous experiment, because there you have shown an increase of M ratio, decrease of M ratio with increasing D prime. And here you have the three contrasts, which should actually give rise to different D primes, right? Because like they're more or less difficult. And here you see that the M ratio is constant between the contrasts, even if the D prime changes somehow.
Yeah.
Yeah.
I think in a way you're helping me here to sort of answer this question before. Yeah. So if you have a manipulation that changes the signal, which is most manipulations out there, and I think no matter what you do, you actually end up changing the signal. And here we manipulate the contrast. We think that actually changes the signal, and if so, M ratio is unaffected. But if you have manipulation that is able to change the sensory noise, then you would see what we saw in the previous study. Again, we don't have a separate measure of the internal representation, so I can't really prove this at this point. But this is what I strongly believe is happening.
Okay, thanks.
All right, so can we use this metacognitive noise measure, this metacognitive noise parameter as a measure of metacognition? So let's first apply this to the Gaussian metacognitive noise. If we do that, what we see is that, again, just as M ratio, the sigma meta doesn't depend on contrast, so that's great. So we have another measure that doesn't vary with accuracy or with difficulty, but it still has the exact same thing. So M ratio decreases with higher confidence criterion locations, and this measure of sigma meta increases. So it's sort of the opposite effect, but it's still biased. So you can run the statistics, and the confidence criterion location is statistically different, highly different for the different locations. But when you do that for the log normal meta-noise model, now all of a sudden you see that it doesn't vary either with confidence criterion location or with contrast. And we have also run Bayesian statistics here to show that there's actually positive evidence for the null hypothesis that these things don't change with either accuracy or with contrast. So to have an interim conclusion for this part, process models and measures of metacognition are intrinsically linked. So I think this is a really critical point. And the log normal model may be actually a pretty decent model. So I see that I'm sort of running a little bit longer than what I thought. So let me just tell you relatively quickly about the next two things, and maybe we can hold off questions until the end. So
I think that sounds good. We've got plenty of time, but maybe, yeah, any substantive questions we can leave to the end now and let you get through the next couple of things, and then have some time for Q&A.
Yeah. All right. So then we were like, okay, well, we have a model that we showed it's better than two other models, but is that really a model that actually works better than most models? So we were like, well, let's actually do a big model comparison. So we gathered all of the models that we could find in the literature, and we found 12 of them. So I'm not going to go through this. I think probably some of you are familiar with some of these, and maybe some of you are not familiar with any, but it's just way too much to give you the rundown of all of these models. But the point is, we wanted to compare all existing models of metacognition that are models of choice. There's some remaining models that are models of reaction time that we couldn't do anything with because we're just fitting them to choice. We want to compare apples to apples. But I do want to mention that 2DSD is also a reaction time model, but we're actually able to sort of to still fit it to just choice data without any loss of without any loss. So here's what we did. We used two experiments with really large data sets. So experiment one, there was this X and O task. People need to say whether there's more X or O's and give confidence rating. Most importantly, we had a ton of trials per subject and just one difficulty level. So that will be important later. This is data set collected by my graduate Nadia Khadara, and it's part of a upcoming science paper where we talk about how feedback doesn't affect metacognitive sensitivity, at least trial by trial feedback. Experiment 2 is the same data set that we used before. So that's the data set that I already showed you. So then we fit all 12 models. We did a lot of things we did a lot of exploration of these models that people haven't really done before. So for example, we did model recovery. Like, can you recover the different models when you generate data from one model and then fit all 12 models, can you recover the same model? And you can see that you do pretty decently. There's a few exceptions. Things a little bit worse for experiment 1 that has a single difficulty level. Once you have 3 difficulty levels, that helps model recovery quite a bit. And there's a few exceptions that are very interesting. But let me tell you sort of the main results. So the way we're going to plot it is the least likely models are going to be on the top, the most likely models are going to be on the bottom. So that's a little counterintuitive, but the good models are on the bottom. And here's what you see. So we've normalized so that the log norm, the best model is at 0, and higher numbers here mean worse and worse models. This inset is just to show you a little bit better what these 4 models are. So you can see that the log normal model, the log n, actually fits the data best in experiment 1, as well as in experiment 2. So this with using AIC, we've done the same thing with BIC, which is a slightly different measure that penalizes the number of parameters in a different way. But again, the log normal model is the best in terms of explaining these data. You can also look at model frequencies. So this measure P model, and the log normal model again is the best. And this inset shows the protected exceedance probabilities, which is a measure of what is the most likely model in the whole population of subjects. So for both of these experiments, the log normal model is close to 1 in terms of the most likely model across all subjects. Now, this is really a big project. We've done a lot of different things here that I'm not going to have time to show you. I just want to show you one more thing, which is we try to understand why some models do better than others. And it looks like the most critical feature is how well these models can predict. So on the y-axis here is predicted M ratio, meta d prime divided by d prime. On the x-axis is observed M ratio. You see that a bunch of these models actually can't really do anything decent with M ratio. So they just predict either that M ratio stay at 1, signal detection theory, positional model, or at around 0.5 for the positive evidence model. And the rest, the models that actually do better in model comparison, they predict better the metacognitive sensitivity or metacognitive efficiency. But again, there's a lot of interesting insight here, but you should really get Michael to give a talk to you so that you learn more. So the interim conclusion here, the log normal meta-noise model outperforms existing models of metacognition. Right, so finally, and this is going to be the most speculative part, I now keep this short. I want to just speculate about, is the metacognitive system separate from the decision-making system? And this has been something that all of this modeling work has really made me think more and more about. So as a field, I feel like we tend to assume that these two things are separate. And I've been trying to think, where does this come from? And I'm not sure where to locate it. But I think probably a really influential paper is Nelson and Naren's 1990 that sort of really emphasized this concept of meta level versus object level and these two things being different. And they mentioned 3 different principles. And the first one is that the cognitive process is split into 2 or more specifically interrelated levels. So the signal at the object level is different from the signal at the meta level. This has been tremendously influential. So let me just show you some of the papers from, some of the models from the literature. So this is Fleming and Daw. You have the worst state that gets split into decision and confidence. You have Pascal and Massian. The evidence gets split into sensory evidence and confidence evidence. The work of Manscapel and Lau, different models. You have different noises in a dual channel model or different noises in a hierarchical model. And just to be clear, we're in the same boat. The model that I was showing you from just 2 years ago, we were assuming that there's a meta level that is separate from the decision level. And if you look at all of the models, I would say that it's only signal detection theory, which was developed way back in the day, and it was never a model of metacognition. And I would say this new log normal model sort of really assumes that the signal is the same for decision and confidence. That's sort of the most natural interpretation of both of these models. For these next 4 models, either interpretation is possible. I think people still tend to to take the interpretation of the different signals. And for these other 6 models, maybe again, for some of them, you could interpret them as the signal is the same, but they're typically interpreted as the signal is different. So we definitely have this bias in the field that the signal is different. And that causes, that leads to like statements like, you know, in this really important, really great paper that introduced meta D prime, Manskau and Lau say, we call our measure meta D prime, which reflects how much information in signal to noise units is available for metacognition. Idea being that there's an object level, there's a meta level. At the meta level, you know what you're measuring, your measured M ratio shows you how much information is there. So so it's a separate level, right? It sort of, this only makes sense if you think of metacognition as a separate system. And just to show you that I'm not throwing just them under the bus, I'm also throwing myself and Steve under the bus here, because, you know, we signed off on this. At least I did. I don't know. Maybe he criticized them and they didn't take his advice, but I didn't about this statement at least. So why assume 2 systems in the first place? I've been trying to think about, you know, why do we do this? And I think honestly, the most important reason is it's intuitive. This is just, it just makes sense, right? There's, when you think about, am I correct? It just seems to be a higher order thing. But, you know, that's not the best scientific argument, right? Many things are intuitive and wrong. So I'm not going to say anything more about this. I think there's better arguments to use for why this could be the case. So confidence, as I said already, is inefficient. So it's less informative than the choice. But the thing is, confidence is also a more difficult computation. So it's easy to think of ways why these kind of findings can be due to computation rather than to the signal itself being different. Then there's, you know, findings, and this is probably the best evidence for this kind of idea of 2 systems. You know, you can use TMS or lesion to prefrontal cortex that can affect confidence but not accuracy. And there's you know, a whole bunch of evidence that this kind of stuff happens. The issue here is, again, it's, well, confidence is a more difficult computation, so maybe it's just easier to disrupt it compared to the decision. So just this by itself, it's hard to see this as really strong convincing evidence by itself. On the other hand, why assume a single system? Well, a priori, it's a more parsimonious explanation, right? You usually postulate this 2 things if there's a really good reason. And turns out, well, it doesn't seem like there's a good reason, right? So you look at all of these computational models, you know, the 12 different models, none of the ones that actually assume that necessitate 2 different systems actually do better in model comparison. So if those models don't fit better, then why assume as, you know, 2 different systems? You can also think about the empirical phenomenon. There's a lot of dissociation between accuracy and confidence. Every single one of them that I'm aware of can be explained as a computational failure rather than as a signal failure. And finally, there's actually a ton of overlap between the signals for confidence and decision. So they're both in the frontal parietal networks, and it's sort of, you know, here's a recent paper from my group where we compared the decision activations and the confidence activations, and, you know, this pretty much the same brain areas that are involved. And more importantly, they're in the frontal parietal network. Information that is in the frontal parietal network tends to be widely available. It tends to be not in a module that is not available to other modules. And I think this kind of thing actually has very important implications about animal metacognition. So this is not my area, and I'm happy to be criticized as completely ignorant here. But there's a lot of debate on whether there's animals have metacognition. Some people say so, and some people say no, that's not the case. And from what I can tell, the whole debate comes down to, can we use first order explanations in order to explain the phenomena? And the underlying assumption is that for humans, we cannot use first order explanations that the object level system and the method level system, they're different systems clearly, but for animals, we need to prove it. But maybe that's not true for humans. Maybe this is not true for humans. And if it's not true for humans, then this whole debate for animals sort of takes a very different, you can see it in a very different light. All right, I'm sure there's going to be a lot of comments on that stuff. So in the conclusion here, the object level and metacognitive systems may just be the exact same system working with the exact same signal. At least that's what I currently believe. All right, so overall conclusions. Metacognitive noise makes no predictions confirmed by the data. Hopefully that's convincing. Models and measures of metacognition are intrinsically linked. I think this is a really important theoretical insight. And I think as a field, we need to take this more seriously, and we need to like really work on linking our models and our measures. I don't know whether that particular model that we have and that particular measure that we have will be the ultimate, winners or the best things that we can do. That's still to be tested, but I think we need to work in that direction. The log normal model outperform all existing models of metacognition, at least in this simple task that we are using. And finally, the signal for decision and confidence may just end up being completely the same. I want to thank my lab. I have highlighted some of the people whose work I've highlighted. I want to thank the funding resources or the funding sources, and thank you for your attention.
Brilliant. Thank you so much, Toby. So we should first unmute ourselves and give you a round of applause for the great talk. And as usual, we'll use the raise hand tool to signal that you have a question. So please do put your hand up if you have a question to ask. I'm going to kick off with, well, I've got lots of questions, but maybe I'll lead with the more specific one and then maybe ask a more general one towards the end. So, but it's super interesting what you presented in terms of the model comparison. But I was starting to think to myself, okay, a lot of those models that you showed assume Gaussian noise, right? So they have different moving parts, but even the higher order or more complex ones, they've got Gaussian noise in them. So I'm wondering what your finding is telling us is that it could be just that you don't need all that additional stuff, right? But it could be that you've identified a particular noise type that we need to take seriously, and then we can maybe augment those other models and bring in that different type of noise distribution. So I'm just wondering whether you've thought about that or tried anything along those lines.
Yeah, no, you're absolutely correct. So, we thought about for a while, like, all of, many of these models, you can do a lot of different things with them. You can have many different versions of them. And we thought that we need to start somewhere. And we thought we'd start with just fitting the standard version of them. But it's absolutely true. So it could be that, the second order model or positive evidence model or something that is augmented with log normal noise rather than Gaussian noise will actually do better than even our simple log normal model. I honestly am starting to think that we should not be using Gabor patches to be doing this kind of work. But yeah, no, you're absolutely right. So that's why I've tried to say it very carefully. All existing models of metacognition. So new versions of them can definitely be better. So we don't know that this model is, like, in some absolute sense the best model.
Okay, fantastic. Also, I realized we hadn't stopped the recording, so I'm going to stop recording.